Hi there! Resistors are found everywhere in electronic devices. In fact, they are an essential part of them. But what exactly are resistors? Let's explore their characteristics and how they behave. Let's begin by building a circuit to measure the current that flows inside a resistor and the voltage at its ends. So we will put a device here, a voltmeter, to measure the voltage across the resistor, and then we will put an ammeter over here to measure the current that flows through the resistor. R is the value of the resistor. Then we will put a power supply over here, and let's see what happened. So this is V. Let's also create a table where we put V and A, and let's take measurements at different value of the voltage, and let's see how much is the current. So we will see if we can figure out how the resistor works. Let's now build the circuit. So this is a resistor, which is the one that is right over here. So I'm going to put it on the breadboard over here, this way. Okay. Now, on one side of the resistor, I will attach the positive of the power supply, like this. On the other end of the resistor, I will attach the positive of the ammeter, for which I will use this. Now the negative of the ammeter will go to the negative of the power supply. So these will go together. And finally, I will connect a voltmeter between the two ends of the resistor. So I will put the positive on this side, right here, and the negative on this other side. Let's check now what the instruments are reading. We see that the voltage is about 3 and the current is about 2 milliamps. Let's go write them down in the table that we prepared before. So we found that around the resistor there is a voltage of about 3 volts and a current of about 2 milliamps. Now let's increase the voltage of the circuit, the power supply. Let's bring it up a little bit. I have put 6 volts here now, and the reading is now 4 milliamps. Let's write it down on the table. We have 6 volts around the resistors, the current inside of it is 4 milliamps. And now let's increase the voltage a little bit more. Let's put it to 9 volts. And 6 milliamps are the current that flows into it. Let's write down also these values in the table, and let's see what we come up with. If we put a voltage of 9 volts, we have seen that we have measured 6 milliamps flowing through the resistor. Now, do you see anything with these numbers that seems to be following a certain law? Let's look at this. 3 divided by 2. 3 divided by 2 milliamps, which we represent this way, is equal to what? It's 1.5, 3 divided by 2 is 1.5, times 10 to the power of 3. Let's do it with these other numbers now. So we have 6 divided by 4 times 10 to the power of minus 3, which is 6 divided by 4 is still 1.5, and this is still 10 to the power of 3. Let's see if it is true also for this one. This is 9 divided by 6 times 10 to the power of minus 3. 9 divided by 6 is still 1.5 times 10 to the power of 3. So you can see that when we make flow current in a resistor by applying a voltage around it, what happens is the ratio between the voltage and the current in the resistor is always the same number, is always a constant. This is what we call resistance of the resistor, which is a very specific number and depends directly by the voltage and the current that flows through the resistor itself. So for a defining resistor, whatever is the voltage, the current will be such a way that the ratio between V and D will be always R. How can we rewrite this one too? We can say that V equals R times I, or we can put it in this form, I equals V over R. So these are the various ways of writing always the same information. This is what is called Ohm's Law. Georg Ohm was a mathematician. He found exactly this same information, that voltage and current are directly proportional, and the constant of proportionality is this R, which he called resistance. Now that we have calculated the value of the resistor, let's see if we can read its values directly on its body. Here it is. You can see there are 5 bands of colors. There is a brown, a green, a black, a brown, and another brown. If you look carefully, the brown on the right side is a little farther away than the other bands, which means that is a band that refers to the tolerance of the resistor, not to its value. So for now, we don't consider it. Let's look at the first 4 bands: brown, green, black, and brown again. This is the table that allows us to decode the colors on the resistor. So you see there are resistors that have 4 bands, others that have 5 bands, others that have even 6 bands of colors. Our own resistor has a 5 band, so this is our reference point. The first band, if we follow the line, was brown, and brown is identified by the number 1. Let's write it over here. The second band was green. Second band is identified by the number 5. The third band was black. Following the path of the third band, we go to a 0. And the last band, the fourth actually, was brown again. So following the path here, this is a multiplier, see? So this is not a digit that we write down, but this is a multiplier. And brown is a 10, which means that we multiply this number that we just wrote by 10. And the result is 1500, which we can also write as 1.5 times 10 to the power of 3. This is the resistance that we actually found before, right here. And it's measured in ohms, so our R, which was up here, it's equal to 1.5 kilo ohm, or, which is the same, 1500 ohms. This is the symbol, it's an omega, Greek letter, to indicate that the measurements unit for the resistance, which is the ohm, has the same name of the scientist who first discovered the law, and it was called this way in his honor. If you want a table like this, you just Google it, or more easily, you can download it from my website, eleneasy.com. This way, eleneasy.com. Go there, and you will find a post which has a picture of this table. You can take the picture from there and use it at your own pleasure. Let's now study the behavior of the resistors when they are put in a series. 2 or more components are said to be in series when they are traversed by the same amount of current. So if I put a number of resistors like this, I name that R1, R2, R3, and then I apply a voltage to them. Since there is only one loop, there is only one current that flows into this circuit over here, and it's the same across all resistors. So this is the definition of series. What we are going to do, we are going to put here an ammeter, and then we are going to use a voltmeter to measure the voltage across each resistor individually. So we will do it here, across the resistors R1, and then we will repeat across R2 and then across R3. In order to study this circuit, I'm going to write a little table where I'm going to have V1, V2, and V3, which are the three voltages on the three resistors. And I'm also going to measure the current I, which is the same for the whole circuit. So I will write it down just once. Let's assemble the circuit now. Let's build the circuit that we just designed. So we need three resistors. 1, 2, and 3. And we have to put them like this. So I'm going to put the first resistors on the breadboard, like this here. Then I'm going to put the second resistor. And the second resistor is connected to the first resistor on the right side. So I'm going to put this resistor here on this side on the same column as the first one, and the other side in another column here. So these two resistors are connected right over here. Now the third resistor will be the same thing, is connected on this side to R2. So I'm going to put it again on the same column right here and here. So here in this column R1 is connected to R2, and here in this column R2 is connected to R3. So they are all in series. Now let's add the ammeter. So I'm going to put this connector over here. Then I'm going to put this connector to the power supply on the positive side. The other end of the power supply will go to the other end of the series. So it will go over here. Oops, this is disconnected. Let me connect it again a little better. There we go. So now let's power up. And let's see what we have. Oops, I put the resistor in the wrong place. You see, this was supposed to be the place, the column. So, let's see what we have. We can see the current over here. You see 7.6 milliamps. So, let's now measure the voltage on the first resistor. So, over here and over here, and the voltage is 1.67 volts approximately. So this resistor has a voltage of 1.67 volts at its extremities, and it's crossed by a current of 7.6 milliamps, which is the same current that goes across all the other resistors too. So let's write down these values now. We just measure the current that we will round up to 7.6 milliamps, and the voltage across the first resistor R1 is 1.67 volt. Let's take now the next measurement. Let's move the voltmeter to the second resistor. Let's see what we read over here. So the current is about the same, about 7.6 milliamps, and the voltage again is 1.67 volt approximately. Let's write down these new values now. Again, for these measurements, the voltage seems to be the same. And finally, let's put the voltmeter across the third resistor. And let's measure the value over there. For this, the current of course is always the same. And look at that, also the voltage is also the same. Let's write down these values, this one in particular, 1.67 volt, and let's see what we can come up with. For these last measurements, again, we are going to have 1.67 volt. So, let's see what's going on over here. Remember, we have said that the voltage across a resistor is equals to the resistor itself, to the resistance of the resistor, multiplied the current that flows through it. In this case, this is the Ohm's law. In this case, we have the voltages and we have the current, so we can calculate the resistance. So for R1, the resistance is V1 over I, which is 1.67 volt divided by 7.6 milliamps. And this, if you use your calculator, it's about 220. If we do the same calculation for R2, we will see that V2 over I, again, is the same numbers, 1.67 volt divided by 7.6 milliamps, equals, again, 220. And the same for R3. It's 220 ohms. So, as you can see, all three resistors have the same value. And we can check them out, actually. Let's pick them up, the resistors that I used in the circuit, and let's see what their value is. Remember, we want to use this table. So, here is our resistor. And we have a red, and then another red, a black, and a black. So the first red means 2. The second red, the second column, means again 2. The black on the third column means 0, so 2, 2, 0. Let me write it down here. We have 2, 2, 0. And then the fourth band is another black, which means multiplied by 1. So the number is 220, which is exactly the value that we calculated. So done with this resistor, let's check the other one I used. And here we go. Let me pull it up from the circuit. Here it is. And again, as you can see, there is a red, red, black, black. So this is the same resistor, 220 volts, 220 ohms, sorry. And then the last one, here we go, it's red, red, black, black, another 220 ohm. So you see, the calculations that we have done based on the measurements that we took reflect exactly what the value, the nominal value of the resistors is. I'm going to draw now a different kind of circuit where this time all the resistors receive the same amount of voltage from the power supply. So I'm going to put a resistor over here, R1, which receives the voltage V, and then another resistor here, which I'm calling R2, and which receives again the same voltage from V, and another resistor here, R3, which again receives the same voltage from V. So as you can see, the generator V will make the current flow over here, and there will be a certain amount of current that goes in the first resistor, a certain amount of current that goes in the other resistor, and a certain amount of current that goes in the last resistor. Let's call the first current here I, I1, I2, and I3. And we are going to create this circuit, and we are going to measure all these currents, and we are going to write down the values over here. Then we will talk about the results of these measurements, what they mean. Note that in order to measure the current across the resistors, across the voltage, I would have to break, for example, for measuring the current I would have to break the connection over here and put in between an ammeter right in here. And I would have to do the same for each resistors. In order to measure each of the current I1, I2, and I3, I would have to break the circuit, put the ammeter in place here, and take the current over here. I would have to do it the same here and the same here. I will take these 4 measurements one at a time. Let's now build the circuit that we just drew. So, if we look at this picture, we have 3 resistors, all of them connected from one side to the positive of the power supply, on the other side to the negative of the power supply. I'm going to use the rails here, the power rails, on the breadboard, and so I will connect the resistors that way. And take the first resistor, I'm going to put it on this side on the positive power rail over here, and on the other side I'm going to put it right here, there, and from there I will connect it to the negative power rail through this and over here. Why I'm using this cable? Because this way I will be able to break the circuit and put in between the ammeter, like we said before. So let's do the same with the second resistor. So positive power rail, this column here, then this wire connected here on the same column, and then on the negative power rail. And then the last circuit, the last resistor in the circuit, again, positive power rail here, and column here. I need to put shit inside, well. And then another wire, and we connect the same column to the negative power rail. Now I'm gonna use these pins to easily attach my alligator clips to the breadboard. So this goes to the positive power rail and this goes to the negative power rail. So this is my power supply. If I attach the negative over here and the positive over here, my circuit is closed, and now the current is supposed to go through all the resistors. If I want to measure it, I'm gonna take these clips from the ammeter. I'm gonna break the circuit right over here on the top. So here, I will put here the ammeter, and the other end of the power supply will be connected to the ammeter. So the ammeter basically will sit here, just in series with the power supply. As you can see, we read about 21.2 milliamps. So 21.2 milliamps is the current I that flows through the power supply into the 3 resistors. Let's write this down. The first measurements give us a value that is approximately 21.2 milliamps. Okay, now back to the circuit, and this time now we disconnect the ammeter from this place, which is the power supply. We will put the power supply on the right place over here, and then we will connect the ammeter. I'm gonna put it right over here, breaking the circuit between R1 and the negative rail. So I'm going to break the circuit over here, and I'm going to put the ammeter in between. So the ammeter will go here, and will go to the power rail, right here. There we go. So now the current that the ammeter is showing is the current that flows only in this resistor, because we have put the ammeter in series with the resistor. And the current that we see here is 14.8 milliamps. Let's write down this value too. The measurement just taken, it's about 14.8 milliamps, and this is the one that flows through resistor R1. Now let's measure the current in the second resistor. So we have to disconnect the ammeter from here, put that resistor back to the negative rail. This time we will disconnect the second resistor from the negative rail, and we will attach the ammeter right over there. So now the current that will be shown by the ammeter, measured by the ammeter, is the one that passed through the second resistor. Let's see the value. Is about 4.5 milliamps. Let's write down this value too. 4.5 milliamps. Okay, now finally let's measure the current on the third resistor. I'm going to do the same thing. Disconnect the ammeter from the second resistor and put back the second resistor to the negative rail. Disconnect the third resistor from the negative rail and connect it to the ammeter. So now the ammeter measures the current only in this resistor, and the value is 2.2 milliamps. Let's write down this value, which is 2.2 milliamps. Now, what can we say about this? If we look at this picture, it looks like the current here flows in this branch up to here, and then here splits. A piece of it goes to I1 and the rest continues over here. And then another piece goes to I2 and the rest continues over here, which is the I3 itself. So it seems like the current I, it's given by the sum of the three current I1, I2 and I3. Let's see if that is true. Well, it's very simple. If we add up these values, 14.8, 4.5 and 2.2, we end up with 18, 19.3, 0.5, 21.5, which is very close to the number 21.2 that measured at the beginning. And makes sense because, of course, we have to keep into account when we do these kind of things the error that we committed for each measurement. Let's look at something else now. If I want to calculate the current I1, I2 and I3 that flows in the three resistors R1, R2 and R3, I could use Ohm's law. I know that the voltage at the two ends of each resistor is V. I know the value of the resistors, so I can calculate the current like this. I1 equals V to R1, Ohm's law, right? And then I2 equals V, again, divided by R2. And the same for I3, which is V divided by R3. So, if I substitute these values over here, I find that I equals V over R1 plus V over R2 plus V over R3, which I can also write as V times 1 over R1 plus 1 over R2 plus 1 over R3. Now let's take a moment and think about Ohm's law. If I have a current I and a voltage V, and the voltage V is applied to a resistor, and the current I flows into it, I would have, by Ohm's law, a thing like this. Right? But now look at this and look at this. Don't they look similar to each other? if I, instead of this R, put all this stuff here, it's basically the same thing. I mean, if I substitute for 1 over R the 1 over R1 plus 1 over R2 plus 1 over R3, these two things are exactly the same. So this thing here, this equation, is the one that identifies the equivalent resistor for parallel circuits. These are parallel circuits. This is a parallel of resistors because they all receive the same voltage. By definition, two or more components are in parallel if they are powered by the same voltage. So the R equivalent will be 1 over R1 plus 1 over R2 plus 1 over R3. So this is the final value. So now we have this information, the voltage over here, which we know it's 1.5 volts, because that's the value that we set on the power supply. And then we have the currents. So if I calculate R1 as V divided by I1, I obtain 1.5 divided by 14.8 milliamps, so times 3 to the power of minus 3, and this is equal to about 102 ohms. Ohm is the measurement unit for the resistors. Same way, R2 is going to be V over I2 equals 1.5 divided by 4.5 times by 10 to the power of minus 3. And this is about 335.6 ohms. And finally, we can calculate R3 as V over I3, which is 1.5 divided by 2.2 milliamps. And this is equal to about 686.4 ohms. If we now go check the resistors that we put in the circuit, let's see what we can find. This is the first one. These reds, brown, black, black, black. If we look at our diagram, brown means 1. So let me write it down over here, 1. Then the black in the second band means 0. The black in the third band means again 0. And the black in the fourth band means times 1. So it's still 100. So this resistor is 100 ohms. Let's go on and measure and look at the second one. It's orange, orange, black, and black. Yes. So let's see. Orange on the first band is 3. Orange on the second band is another 3. Black on the third band is a 0. Black on the fourth band is times 1, so still this number. So this is 330 ohms. Let's take a look at the last one. So this one, the other way, we have a blue, then we have a gray, and then a black, and another black. So blue means 6, and then gray means 8, and then black on the third means 0, and black on the fourth means multiply by 1, so it's still 680. And this is the resistance of this last resistor that we put in the circuit. Let's compare with the values that we calculated. Look at that. 102, 100, 335, 330, 686, 680. You can see that the values almost match, and of course little differences are because, from one side, because we made, of course, errors when reading the numbers, when making the measurements, and also because each resistor has its own tolerance. If you recall, the tolerance is the last band. In the case of our resistor, which are 5-band color code, is the last one. And if we take a look at each resistor, it's always brown, because that's the kind of resistors I had. And brown in the tolerance means plus minus 1%. So, which means that for this one, for example, the value 100, that is the nominal value of the resistor, can really be anywhere between 99 ohm and 101 ohms. For this one, it will be 3.3, the 1%. So this resistor will be anywhere between 326.7 and 333.3. There are two things I want to show you still about resistors. Number one is the power that is dissipated over a resistor, and the other one is the maximum voltage that a resistor can handle. Each resistor, when put in a circuit, is subject to a certain voltage. Now, the voltage cannot exceed certain values, because otherwise the resistor would break because of too much electric field in between the two ends. However, even for resistors so small, which this is basically 1/8 of a watts in terms of power, the rating in terms of voltage for resistors like this is around 200, 300 volts, something like that. In normal electronic circuits, you will never have this kind of voltages. Voltages more likely will go in the term of 1 volt or even less on a single resistor. So basically, you never hear in general about voltage ratings for resistors, because for normal applications there is no need to. However, know that there are this kind of limitations. So if one day you are going to work with high voltages, let's say above 200 volts, know that you have to use the right resistors, otherwise they will break, they won't work anymore. The other thing about resistors is the power. I already said that this resistor has a power rating of 1/8 of a watt, like this. P equals 1/8 of a watt. There are resistors that have 1/4 of a watt, half watt, 1 watt, 5, 10 watts, depending on the kind of application, how much current goes through the resistor. Why I'm saying that? Because the power in electric terms is expressed by the multiplication of voltage times current. So, if I apply a certain voltage at the ends of a resistors and it flows a certain current through it, the power that is dissipated by the resistor, it's equal to the product of these two quantities. By Ohm's law, we know that we can rewrite this in another terms. Instead of writing I could write V over R, right? So this can be expressed also this way. this is still the power dissipated by the same resistors. So if I apply, for example, 10 volt on a resistor that is 1 kilo ohm, 10 volt over 1 kilo ohm, I would have 10 to the powers of 2 divided by 1 times 10 to the power of 3, which is about 0.1 watts. A resistor like this is perfectly fine with something like that, because it can dissipate up to 1/8 of a watt, which is greater than this. So it's fine. Another way to calculate the power dissipated by the resistor is changing, instead of substituting the I in this equation, we substitute V. So I'm going to write this way. V is R times I times this I means R times I squared. Same thing. So if I know a voltage and current that goes to the resistor, I can calculate the power this way. If I know only the voltage, I calculate it this way. And if I know only the current, I can calculate it this way. There is always a way to do that, but it's always the same number that comes out. What happened if I used resistor in a circuit where I exceed the power rating of the resistor? The resistor will break again, like in the case where we apply an excessive voltage to it. Let's see now what happens when we make the resistor dissipate more power than he can actually handle. We will do this using this resistor, which is so brown, black means 100 ohms. Brown is 1, black 10, under the black 100 times 100 ohms. So we're going to use our 100 ohm resistor, and we will connect it directly to the power supply here and here. As you can see, the voltage is 1.87 volt, and there is about 12 milliamps of current going through the resistor. Let's see what happens now once we increase the voltage. Let's go up to around 5 volts. Let me touch it. Let's see. It's getting warm because it's dissipating all that power. Let's keep bringing it up. Now we are around 10 volts. You see the current is increased considerably. Now the resistor is definitely hot. Look, it's smoking now. It's burning out, which means it won't work anymore. So let me disconnect this. There we go. So you see, if you don't pay attention what to do with a resistor, how much power you make him dissipate, the resistor will badly burn, and at the end it won't work anymore. I hope you had fun following this video and that you found it also interesting. If you liked it and would like to see more, please support my channel by subscribing to it. It is just a click away. See you next time, and happy experiments!